right, welcome back everybody. Today we're looking into how to implement BERT based on the transformer architecture from scratch. So in the last lecture we saw how transformers work, how the attention mechanism works, and how BERT is trained using a bidirectional architecture. It's an encoder only model, and it's trained to basically predict corrupted tokens from a sequence, which we will use mask tokens for. And there's several other tokens, the padding token and the CLS and separator token. So we will implement this with PyTorch today. And the first thing we do is we import a bunch of things from there. So we import math, regex for filtering the text. If you're not familiar with regular expressions, there's plenty of tutorials for that. From random, we import everything. We just need a few functions to randomly sample text. Then, of course, NumPy to use arrays and matrices, and Torch. And from Torch, we also import the NN neural network part and the optimizer part. So if we import that, the next thing we do is we create some training data. So this is not very close to reality, but since we have limited compute capacity now, we just use some random text. So here we have a few sentences. Hello, how are you? I'm Romeo. Hello, Romeo. My name is Juliet. Nice to meet you. And you can see that each of these sentences in this tuple, they are ordered. So the first one is the first one in the actual play, and then the next one is the following one. So we have a structure. This is actually from a document, and we have a separator for the new line. Let's just generate this. And now we would do some pre-processing as we do in many applications. So the first thing we do is we use a regular expression to extract from the text certain special characters that we don't want to take into account, that we don't want to mask. And we also lower the text. So all of these are now not capitalized anymore. And then we split them by the new line character. So we get sentences. And then we create a word list, which we use a set of each of the words in the sentence. And this set will contain all the different words that we split. And that's all the words that exist in our data set. So if there's a new word, we would not know it, but all the words that existed here in this document, they're here. And then we also create a word to ID dictionary that maps our 4 special characters, which is the padding one, the CLS one, the separating one, and the mask one. And we'll use them later. And then in the word list, we assign each word also an ID. And of course, we offset it by 4, simply because here we have already 4 tokens. So if you want to make this more generic, you could use the length of the dictionary keys. So you could do something like this, word to ID dot keys, and there's 4. So this should be 4. Okay, and then we do the reverse dictionary too. We map the IDs to words as well, just to encode and decode. So if we want to encode a sentence, we use the word to ID. If we want to decode a sentence, we use the ID to word to get back to words. And then we also have a vocabulary size. That's just the length of this dictionary. So actually, you don't need to do keys here. You can also do the length of the dictionary. Will return how many keys are in there. We create another list, token list. And this here, we will have all the different, encoded tokens. So here we use the word to ID on all the different sentences that are split into words. And then this token list will contain all the tokens. Okay, and then we can see the token list. And now the token list contains the IDs, exactly the IDs from before. Actually, now that we use the length here, there's a small bug you can see. Why this bug happens is the word to ID changes, right? So this will grow when we assign more words. So this actually has to be 4. Before, if we want to make it more generic, we can just say the length of word to ID. This is our offset. And now we use the offset. This is a silly bug. So don't do this. The offset has to be computed before, because the word to ID dictionary changes, and so will the length. So now if we do this again, now we get the correct IDs. And these IDs are just the token IDs from the text. So hello is 28 here and here, and it's also here and here. So now that we have this token list, we can map all the different words to actual IDs. And then in the next step, we can map the IDs to embeddings. Let's define a few hyperparameters. So the maximum length of the sentence and number of words, we set it to 30. Common configurations for pre-training are 512. 512 we'll see later, divided by 2 or multiples of 2 makes the model more efficient. Otherwise, we would have to pad more. In this case, it doesn't matter. We just use 30. Also, 128 is an option used for efficiency. Then the batch size 6, usually it's like a multiple of 2 again. We can do 8. In our case, we just have 6 sentences, so it doesn't make much sense. So the number of concurrent examples, the batch size, we'll see this later. The number of tokens to predict is 5. Then we have some configuration for the BERT model, the number of layers, the number of heads for the multi-headed attention, the embedding size. These are actually values from BERT. The scaling dimension of the feed-forward network, and the dimension of the key and query, as well as the value. And then the number of segments. The segments are just, if you have 2 sentences, you would have something like CLS. Here's the first sentence. And then you have a separator, and then here's the second. And then you would have more, like here's the third. In our case, we only have 2 sentences. Why is that? Because we want to see which sentences are following another. So there's always 2. Is the sentence the next sentence? Yes or no? So there's 2. Some applications, they have more, but in the pre-training, there's only 2. So you can scale this n segment up, and then you can see what are the differences between 3, 4, 5, 6, 7 sentences. You might want to see if there's a hypothesis in the first sentence and there's 2 statements, and you want to know if one of them is contradicting and one of them is confirming. For example, you can find applications to use multiple segments. We have 2. Okay, and then now here comes a large function, but don't worry, it's actually just a preprocessing function. And what this function does, first, we define a list of a batch. The function will create a batch. And then we define an integer that counts how many positive and how many negative examples we have. What does it mean? Positive means the next sentence is the following sentence, or the second sentence is the following sentence, and negative means the second sentence is a random sentence. So we have a while loop that says as long as the number of positive is not equal to the half of the batch size, or the number of negative is equal to half of the batch size, then we have enough examples in the batch. Then we randomly pick sentences. So we pick one sentence A and one sentence B. And then we use the actual token list, which is the list we computed before. If you look back, the token list here contains the encoded tokens. So that's already the token IDs. So we take the token list and then we concatenate them with a separator and CLS token. So we start with the CLS token, as said before. Then we put the tokens A, the separator, tokens B, and the separator. And of course, we want to convert the words to ID again. So later we can use the actual embedding. Then we generate the segment IDs, which are 0 for the first and 1 for the second sequence. And then for the third can be 2, for the fourth can be 3, and so on. They just tell us where each sequence is. And then here we do the actual masking. So what we do here is first we look at the max predictions, which we defined before. Here is 5, the max number of tokens to predict. And we take the minimum of that and the maximum of 1 and the number of input IDs times 15%. So in case the number of input IDs times 15% is below the max prediction tokens, we take that. If it's above, we just take the max. So it might be that the sequence has 5 terms. And in this case, we would only have 1 token to replace. So we would take this here. It's the minimum. It would be only 1. But in case we have 200 tokens, this will be larger than 5. And we take the 5 because that's the maximum we want to predict. And then the candidate mass position we compute by iterating over the input IDs And then if the token is not the CLS and not the separator token, it is a candidate. We don't want to mask these tokens because either they're too easy to predict or they don't have context. So we want to iterate over all the other tokens and make them the candidates. And then we shuffle the candidates' positions. So then we create two new lists, the masked tokens and the masked positions. Later we need to know where it happened and also which ones are masked. And we iterate over the candidates that are just the tokens without CLS and separator token. And we take the n prediction tokens that we defined before. So we cut this list short to only have the number of prediction tokens that we want. And then here we append the position of this token and of course also the actual token. And in case of 80%, that's if we think back how BERT does this, 80% of the time, we replace the candidate with a mask. 10% we replace it with a random word, and 10% we don't do anything at all. So here this is a bit tricky. So we want to say 80% of the time we do this, and then here the remainder is 20%, and of that 20% we want to know 50% of the time, which is then 10%, we randomly replace this token. Okay, so the reason why here there's not 10% is simply because here we already cut short 80%. So here we would take 10% off 20%. Does that make sense? So if we take 50% off the remaining 20%, then we're at 10. So 80% of the time using the mask token, 10% of the time using a random token, and 10% we just don't do nothing. We just leave the token as it is. Okay, so now that we created the token list, added the separator classification token, added the segment IDs, masked the token, we still need one thing, which is the zero padding. So since these networks have a specific target length, which here we have of 30, the input expects to be 30. So we need to pad the remaining sequence. Okay, we take the maximum length minus the length that we have in the sequence, and the rest we just put a 0 in the input IDs and a 0 in the segment IDs. So we fill this to 30, but the remainder will just be discarded. Okay, and then of course we also have to provide an attention mask later. So, first we have to also identify the sequences that are the next sequences and the sequences that are not the next sequence. So, and we do this 50% of the time we say it is a positive one, and 50% of the time we say it is a negative one. So, in the positive case, we just append it and give the mask token, the segment IDs, input IDs, and positions. And we also give this true, which then tells us, okay, this is actually positive. And we set the positive counter up. And in the other case, we do the same thing where we give false and then the negative counter +1. And later, the mask token positions and the mask tokens will give us, those will be the positions in the model that we predict a token. Okay, and that's it. We return the batch. Let's run this. And now, I was one step too early. Now we get the padding mask. So here in this case, what we do is we take the sequence for the query and the sequence for the key. And from that, we take the batch size as independent, and then the length of the query and the length of the key. And then for the pad token, remember, this is when we set the tokens on the padding here as 0. So here we put the 0 times the number of padding, and here as well. So those are the padding tokens. If we look back here, we define this in the special tokens up here. Padding token is 0. And those tokens, we don't want to compute anything in the network. It would be a waste because these tokens, there's nothing. It's just to make the input length uniform. And in this case, what we do is whenever this is equal to 0, we just unsqueeze it and we expand the mask. And what that will do later is we don't have to multiply anything there. It will just be disregarded. One thing we also have to define is the activation function, which is the GALL-E function. For more details, you can look it up online. This is a variation of the ReLU function, but it takes the cumulative distribution function of the standard normal distribution and then has some constants there. Then we create a batch by our function make batch, and we extract the input IDs, segment IDs, mask tokens, and so on. And we can actually look at this, how it looks like. And now we have a multidimensional input ID array, which is the batch size times 30, right? 30 is the max sequence length, and we have 6, which is our batch size. So this is batch size times sequence length, and the sequence length is 30. And all the zeros you see here, those are the padding positions. And then the segment IDs, they are 0 for the first sequence and 1 for the next, and then the rest is again padded by 0. The mask tokens, those are the actual tokens we changed. There's a maximum of 5. Some of them have 3, 2, or 1. They can vary, but can maximum be 5. And then, of course, for each mask token, we also have the mask position. For half of the sequence, we have the sentence being the next, and for the other half not being the next, as we've seen in the function. And now we can also get the masks. So here, the masks say that the first sequences that are actually tokens, they're not masked, and the remainder is masked. Okay. So now we can set up the embedding space, which is the first layer of the model. And here we have 3 embedding layers. One is for the tokens. So each token gets an embedding. We have a vocabulary size times the demodel size. So each token has an individual embedding. Then we have the positional embedding, which is for each position in the sentence, we have a different embedding. So the first word has a different embedding than the second and the third. But it's not that high of complexity. It's limited to the number of words in the sentence. And that means this positional embedding will let us know at which position the token is. And then we have the segment embedding. That's just the number of segments times the model size. And that's 2 times the model size. And then we have some normalization. And the same way in the forward layer, we apply this. So for the position, we take the positional embedding for the token embedding, and so on. And then we compute the total embedding by just adding them up. So the information is represented in a final embedding that contains the information of all of them. And now we can finally come to the quintessence of attention of transformers of BERT, and that is the scale dot product attention. And we just apply the formula here from the paper that we've seen in the lecture, and that's we take the query times the key. That's here the matrix multiplication. We normalize it with the dimension size. That's just a constant to normalize the layer. And then here we do a mask filling with the attention mask. And that's exactly here what we've seen before. And we only use the non-zero part of the attention mask. So here we want to make sure we don't compute anything that is not a token. When we have filled the masked scores to disregard them, we apply the softmax function to the scores, and then we compute the final sum, the final multiplication, which is the sum of values, and that's the softmax applied to this function times the values, and then we turn back the context and the attention. And then we can basically build this and make one attention. We build an embedding, we apply the embedding to the input IDs and segment IDs. Then we get the attention mask and we apply the scale dot product attention, which gives us the masks and the attention. And if we do that, we will find a layer that contains the attention scores for this network. And there's a bunch of zeros simply because those are the padded ones. And there's a bunch of other scores that are the forwarded values. So to do this for a multi-headed setting, what we need to do is we need to include another dimension n heads. So now there's not only this dimension of the key and the value, but also times the n heads. So this grows to be larger. And then each of these WQ, WK, WV now are or will get 4-dimensional. You have the batch size, you have the number of heads, and then you have the length of the query and the key, or key and value respectively. And when you multiply that, you will have the same thing in the scaled dot product attention, but now applied to another dimension, which is the number of heads. And if we compute that, we will basically do the same as above. We apply the scaled dot product attention to these multidimensional queries, keys, and values. And then we do some reformatting of the dimensions, and then we apply a linear layer on top of the context. We also apply a residual connection to the one before, and that's it. That's the multi-headed attention. It's a bit more complicated to get into this, but once you have figured it out that you just need one more dimension and you need to unsqueeze the masks and repeat them, it's fairly easy to understand. It's basically the same thing as the scaled dot product attention, which we apply here, just to a multi-dimensional scenario. And we can also apply that, and now we'll see that we'll get attention masks the same, but for multiple heads. So before we had one, but now we have this for multiple heads. Okay, the last thing is pretty easy. This is the feed-forward net. This is actually quite crucial, but it's fairly easy to implement. The only thing this does is scaling it from the model dimension to a higher dimension and then back. So this will allow the model to learn a higher dimensional space, and then coming back, it will be activated with the GALU, and that's it. So we take the current dimension after the attention layer, scale it up to the model dimension, which is higher than the feed-forward dimension, which is higher than the model dimension, and then scale it back. Okay, and then an encoder layer is just a multi-headed attention and a pointwise feed-forward net. And that's basically it. We apply both of this, and we get the encoder layer. And now we have all the things we need to build BERT. We have the different layers, we have the different activation functions, and so on. So all we need is embedding layers, then encoder layers, multiple of those. I think here this is 8 for the current version we were using. Some feed-forward layers, some activations, final classifier. This is the classifier for the actual next sentence prediction, and then you will have one for the mask prediction. And yeah, that's here the decoder. So the classifier is for, is this the next sentence? And the decoder is for what mask token is this? And the forward function will apply the embedding layer, get the attention mask. For each of the encoder layers, it will apply the encoder layer with a mask. Then it will pool the final result, which is now we have an embedding for each token in the sequence, but pooled we only have the model dimension as one. And this is what we will use to classify. And usually this is, as you can see here, the output, the first token. So we can also write CLS. Some models don't have this, which then they do a mean of the output, but BERT is designed to use CLS for classification, and here the logits for classification are just on top of the CLS token, another linear layer, and then the batch size times 2. It can either be the next sentence or not. And for the masked positions, we have something similar, but now we have a token level layer that takes each of the embeddings of the final layer. So you have, let's say 30, in our case, 30 embeddings. And on top of this, we apply the decoder, which will then transform the sequence into the dimension of the vocabulary. So for each embedding of the sequence of these 30, we have the whole vocabulary of 30,000 tokens. In our case, it's much less, but let's say 30,000. And for each of them, you get a score. And the one with the high score is the prediction of the mask token. So that's it. We have the BERT model, and we can train it. We initialize the model. Here, the number of epochs we train, the criterion, which is cross-entropy loss. The optimizer, we use Atom, but you can also use regular stochastic gradient descent. We create 100 batches, which are just repeating the training data. And then we create each batch as a long tensor, so then we can compute it with Torch, and we define a running loss, which is the current loss. And then for all the epochs, or for each epoch, we iterate all the batches. We compute the gradients to be 0 at first. We've seen that before in the last lecture. And then we compute the language model and the classification logits when forwarding this, compute the loss, and we mean the loss for both the language model and then, of course, also for the next sentence prediction, and we add these two losses. So here, this is the mean loss for all masks. So there might be 3 masks. We take the mean of each of the predictions for these masks. And of course, for the next sentence prediction, we add these 2 losses. We add them to the running loss, and then we do a backward step. We compute the gradients, and we optimize, and we take a step in the gradients. If we run that, we'll see that after a couple of epochs, the loss is reducing, and we're now training this model here in the background. This is running on CPU, but if you run it on GPU, it will be much faster. This is not a very large model and not a large data set. But you will see that now after an epoch, the loss is at 2.8, the cross entropy, and then in the next epoch, this will be even lower. So now the model has trained. Actually, the loss went up a bit in the last epoch, but in general, the loss would decrease over time. And we can now use this model and predict some tokens. So if we take one of the batches, we can print the text, which is the text here. And then we can print how this would be encoded. And we can mask some tokens. So let's here mask some of these tokens and then see what happens. So in this case, we mask the tokens my and meet. And the token that was predicted is Juliet, which is not really good. Let's see if we run this again. So here now, since we trained this before it was not trained, I think, now the mask tokens is you, and the predicted mask token is also you. So the model learned to predict the right token. We also not gave it the next sentence, but it predicted it is the next sentence. This is due to the data set being really, really small. So this is not a very practical example. It's just to show how the model works. But still, it predicted the right token just after a few minutes or seconds of training. So all of this is great, but there's easier ways. This has all been implemented before. And luckily, there's libraries for this. So for example, Hugging Face is a great library. It's called Transformers, and we can import the auto tokenizer and model for masked language modeling. Tokenizer is everything we did to map words to IDs, basically, in a very easy scenario. And the language model is everything we did after that. So we can use BERT base model and tokenizer. We can do the same and define the text as we did before with the separator token. Here, actually, we can use the CLS token. And then we can tokenize that text, and we'll get a mapping to IDs as well. And we can mask a text here, replace it with a mask, and then convert the token to IDs. And we do a forward pass with the model. This is a pre-trained model. It will load weights that were trained on many tens of gigabytes of data. And then we can forward this and see what are the predictions and compare this the same way we did before. And now we will see what happens. The predicted token is Romeo and the true token is Romeo. So the model knows what to replace. We can also change that mass index to be 4, whatever, and see now the predicted token is R and the true token is R. So the pre-trained model, of course, is way better than anything we trained here, simply because this data set is all that our model has seen. That's it. Thank you very much for listening. Check out the Hugging Face library. It's the largest transformer NLP library out there. And see you in the next one. Thank you.